Hi students, today we're learning about graphs of rational functions. So this is our first foray into rational functions, so something where you actually have a function divided by a function as opposed to just one divided by a function. Okay, so today all we're focusing on are three types of discontinuities. Okay, so we're going to talk about vertical asymptotes, something called infinitesimal wholes, and horizontal asymptotes. Okay, in this note, we also talk oblique asymptotes, but that is saved for a different video. Okay, so there are four types of discontinuities. Today we're just talking about the three. So it's important that you pay attention to what I'm saying in this video because it's important that you understand not only how to find these discontinuities, but also why they exist. Okay, so first of all, let's just define a rational function. Okay, a rational function is a function that can be expressed as f at x equals p at x divided by q at x. Okay, where both p at x and q at x are polynomials. So those are each polynomials, but there's the division. So that is what makes it a rational function. So an example could be something like this. F at x equals x squared minus 2x plus 1, all divided by x plus 5. Okay, so as long as your top is a polynomial and your bottom is a polynomial, that is a rational function. Okay, so rational functions have breaks or discontinuities when f at x is undefined. So in other words, when there are zeros in the denominator. So these are x values that have to be restricted from the domain. So there's two types of discontinuities that arise from the zeros of the denominator, and those are vertical asymptotes and infinitesimal wholes. Okay, so vertical asymptotes we're already familiar with, but there's one little difference that we haven't talked about. A vertical asymptote will happen at x equals a if q at a equals 0. So in other words, that x value makes the denominator 0, but p at a does not equal 0. Okay, so in other words, the denominator is 0, but the numerator can't be. So it's not enough to just say that a value makes the denominator 0 to say it's a vertical asymptote. You have to also conclude that that makes the numerator not 0. Okay, because if it does, if you get the result 0 divided by 0, then that will be an infinitesimal whole. So this example here, f at x equals x plus 1 divided by x minus 2. If we put in f at 2, that gives us 3 divided by 0. So therefore, that then x equals 2 is a VA, since it's not 0 divided by 0, okay? It's a number divided by 0. So therefore, it's a vertical asymptote. But notice in this case, if we put in 3, if we put in 3 here, 2 times 3 is 6. 6 minus 6 is 0. So you'd get 0 divided by 0. So that is not a vertical asymptote. Okay, that'll be an infinitesimal whole, which I talk about in a second. So to draw this function here, you would draw your vertical asymptote at x equals 2. Okay, this actually also has a horizontal asymptote at 1, which I'll explain on the next page. Okay, and your function would end up looking something like this. Okay. All right. So those are your vertical asymptotes. So same as before, except you have to make sure you're checking that it doesn't give you 0 over 0. Okay, and it is impossible for a function to pass through a vertical asymptote. So you can treat that like a brick wall. A vertical asymptote is something that a function will get closer and closer and closer to and will never actually touch. Okay, the reason vertical asymptotes exist is because you can't divide by 0. So as numbers get closer, so in this case, as the x values to get closer and closer to 2, then your y values will get extremely, extremely negative or extremely, extremely large but you can never actually put in 2 because that would break the function. So that's how you're approaching it. So if you want to test it and make sense of why that's true, try putting like f at 1.999999999 into the function, and try putting like f at 2.00000000001 and see what happens. Okay. So infinitesimal holes. A hole is one exact point that does not exist in the function. So the function actually approaches the hole as if this point did exist, but the function does not exist at this exact point. So there's literally just a hole in the function. It looks perfectly normal around the hole, but then just boop, right at that one spot, there's a hole. So this will happen if P at A divided by Q at A is 0 divided by 0. So if a value makes the top and the bottom, the numerator and the denominator 0, then that's an infinitesimal hole. Okay, and this happens when there's a common factor. So for example, here, if we factor this to x plus 2, x minus 2, you'll notice that there's a common factor of negative 2. So these can actually be crossed out, and I'm just left with x plus 2. So this function is actually just a line, the line x plus 2, except it has a hole at x equals 2. Okay, and that's because if you put 2 into the original function before I factored it, oops, I don't know why it does that sometimes. If you put 2 into the original function before I factored it, you would have gotten the result 0 divided by 0. So the hole then is at x equals 2. So therefore the y value of the hole, I just find, oh, now this is behind my head, isn't it? To find the, I'll write it up here. To find the y value of the hole, you just find what f at 2 is in the rearranged formula. So in that case, it would be 2 plus 2, so 4. So therefore, the hole is at 2, 4 is the hole. So I'm going to draw the hole first. So 1, 2, 3, 4, 1, 2, 3, 4, 5. So the hole is at 2, 4. So I'm just going to draw it as a hole. Okay, and then the line is, it goes through 0, 2, and it has a slope of 1. So it goes through this point, this point. Okay, so it's literally just the exact same line as it would be normally, except it just has a hole right there. Okay? So this can happen in quadratics, this can happen in any type of function. If there's a number that you can cross off like this, there's a common factor that you can cross off, whatever the 0 is of that common factor will create a hole at that x value. To find the y value of the hole, you just sub that number into the rearranged function and see where the point should have been if there hadn't been a hole. Okay? All right, so now we get on to horizontal asymptotes. Apologize there. Which, there's a few different types of horizontal asymptotes we need to learn today. So horizontal asymptotes are horizontal lines that the graph of a rational function gets closer and closer to at either end of the function. Therefore, if the horizontal asymptote is y equals k, then the following can be said about the behavior of the function. So as x approaches infinity, y approaches k, or as x approaches negative infinity, y approaches k. So horizontal asymptotes are all about end behavior. So what is happening at the end of a function's life? So if you have like some horizontal asymptote here, y equals k, then the function is approaching it later on. So it could look something like this and like this. Okay, so now we also have this notation though. We can talk about the direction from which the function approaches the asymptote. So if we say y approaches k plus, that means the function approaches the asymptote from above k. So I could say here, as x approaches infinity, y approaches k plus because I'm approaching it from the top. K negative means it's from below. So over here I could say as x approaches negative infinity, y is approaching K negative because it's approaching it from below. Okay, so because horizontal asymptotes deal specifically with end behavior, the function may still pass through the horizontal asymptote at some point. Okay, so you don't have to draw this, but like if you have some horizontal asymptote here, let's say you have vertical asymptotes here, your function could look like this. So there it's approaching the horizontal asymptote, and here it's approaching the horizontal asymptote. But in the middle here, it could look like a cubic and actually go through the horizontal asymptote. This is actually a pretty common type of rational function. So horizontal asymptotes are different in that you can pass through them. But it's talking about the end behavior. So as the function gets extremely large in either direction, it's going to be approaching but never touching that horizontal asymptote. Okay, but in the middle, it might still touch it. So how can we determine horizontal asymptotes? Well, a rational function has a horizontal asymptote only when the degree of p at x, so the numerator, is less than or equal to the degree of q at x. So I like to talk about it as being top heavy, okay? So if the function is bottom heavy, so in other words, sorry, I'm getting this fixed up. If a function is top heavy, so the numerator has a higher degree than the denominator, then there is no asymptote and no horizontal asymptote. Okay, there's only horizontal asymptote if it's balanced, so they're both the same degree, so like both quadratic, both linear, both cubic, or if it's bottom heavy, so like a linear divided by a quadratic, or quadratic divided by a quintic, or something like that. Those are the two times when there are horizontal asymptotes, so even or bottom heavy. All right. So here's where I was going to draw all that other stuff with approaching K from the top or K from the bottom. So you can write that again, or you can just use the graph, the smushed up one that I did up there. Okay, so there's two cases to consider. The first case to consider is the bottom heavy. Okay, so I call this bottom heavy. All right, that's just my own personal term. It's not a real term. Just how I think of it. So if a function is bottom heavy, so the degree of the denominator is higher than the degree of the numerator, the horizontal asymptote is always y equals 0. Always, always, always. So again, you can get good knowledge marks for memorizing this piece of information, but let's think about why this is actually true, so you can get that critical thinking going. So think what happens as x gets extremely large or extremely small. What happens to a function? So let's say I put in x of 100. Okay, that's getting pretty big. So that would mean f at 100 gives me 101 divided by, okay, if I put 100 in there, then I get, okay, I should just tell you what I get. Okay, if I put in f, here, I'll put it over here. If I put 100 into this function, then I get 0.01. Okay, now why is that true? Because, well, I'm going to get 101 divided by some really big number, because x squared makes that 100 really, really, really big. Okay, so if I put in f at 1,000, I'm going to get 1,001 on the top, but on the bottom I'm going to get some huge number, because 1,000 squared, because I'm squaring it, is so big that even though I have I'm subtracting 3 times 1,000, that hardly matters compared to the fact that I'm squaring here. So here I would get 0.001. Okay, and if I put in f at 1,000,000, I'm going to get some tiny number, like 0.00, how many zeros is that? 1, 2, 5 zeros. 9. So notice what's happening here. As I put in humongous numbers, so as x is approaching infinity, then y is approaching 0 plus, okay? 0 from the top, because these are positive, but they're almost 0. So then I can check out what happens when I put in negative numbers. So if I put a negative 100 into the function, I get negative 0.0096, and f at negative 1,000, that's a 1, sorry, is negative 0.0001. So you can see that as x is getting extremely negative, so approaching negative and infinity, y is approaching 0, but from below. So 0, and then I put a negative. So you can explain why this is true by saying this. So as x gets large, okay, the denominator becomes much larger. I'm just going to say this instead of writing it because it's going to get messy. As x gets large, the denominator is much larger than the numerator. So the size of the denominator grows much faster than the size of the numerator because the degree is higher. So therefore, that's why it gets closer and closer to 0, because your denominator is getting much bigger than your numerator. So like how far apart they are, that gap becomes bigger and bigger, and that's what makes it approach 0. So if you don't understand that, make sure you make yourself a little note so I can explain it to you in person tomorrow. Okay, now, what do you guys think about this, though? If the degree of p at x and q at x are the same, how can we come up with the horizontal asymptote? Well, it's actually going to be the ratio of the leading coefficients. So you got to make sure they're in order there, and then you look at the ratio. So in this case, it's going to be 3/2 or 1.5. So why is this true? Well, think about it. As we put in really high numbers, you're going to multiply like 100 by 3, and then you're going to subtract 5, which isn't that big of a deal in the scheme of things because I already multiplied 100 by 3, and then I'm just taking off a measly little 5. And then I'm multiplying 100 by 2, and then adding a measly little 1. So that doesn't really matter much when I put in 100, right? So I get 295 over 201. Okay, so that's about 1.47. Okay, now these measly little negative 5 and plus 1 matters even less when we put in 1,000, okay? Now it's like 3,000 minus 5, that hardly means anything, right? And then 2,000 plus 1, okay? So then that's 1.497, so even closer to 1.5. Now, come on, like when I put in 1,000,000, okay, like seriously, the negative 5 and the plus 1 have hardly any impact. So I have this number that's practically 3 million. So I just took off a stupid little 5 there. And then a number that's practically 2 million, right? 2,000,001. So that's going to be like 1.499997. So as you can see, the significance of what you're adding and subtracting when you're putting in large numbers is hardly anything. What's most important is the leading coefficients, because that huge number is being multiplied by both of those. So that makes sense that the numbers would get closer and closer to the ratio of the leading coefficients, in this case 3/2, okay, as these numbers get larger and larger and larger. So as x approaches infinity, y is approaching 3/2 negative, because it's approaching 1.5 from below, because it's just slightly under 1.5. Okay, same thing if we go really negative. You can just test one of these. You get 1.53, and then f at negative 1,000 is 1.503. So as x approaches negative infinity, y is approaching 3/2, but from above 1.5. So you put the plus there. So you can write this here too, the reasoning why it's the ratio of the leading coefficients. As x gets large, the negative 5 and the plus 1 become increasingly insignificant. So in other words, the larger that x gets, the less significant that minus 5 and the plus 1 become. So therefore, the function approaches 3 over 2. Okay, that ratio. Okay, if you want to think about a bonus question for this unit, I would like you to describe why, when you have a higher degree divided by a lower degree, that there is no horizontal asymptote. Okay, so that would really show your understanding of what a horizontal asymptote is and why it doesn't exist when the function is top heavy. So the numerator has a higher degree than the denominator. Okay, so that's most of the content for this note. I'm just going to do a couple examples. So we're skipping oblique asymptotes until tomorrow, until the next day's note. So we'll go right to example 1. Okay, find all discontinuities of the following rational functions. Okay, so you're always going to check for all 4. Now a function can never have all 4. Because you can't have an oblique and a horizontal asymptote. Okay, spoiler alert, oblique asymptotes only happen if the function is top heavy, so it's a degree, it's a higher degree on the top. And notice that these are both evenly balanced functions, so neither of them are going to have slant asymptotes. So we always check for the vertical asymptotes first, and you do that always by you set the denominator equal to 0. Okay, so that's how you check for the horizontal asymptote. So in this case, it's 4 over 3. Okay, then you check for a whole. So basically, does minus 4 over 3 make the the numerator minus 4 over 3? No, it makes it a number not 0. Sorry. Does minus 4 over 3 make the numerator 0? It doesn't, so that means there's no wholes. Okay, wholes only exist if you have a 0 of the denominator that also makes the numerator 0. So now I check for my horizontal asymptote. Okay, so the degrees are equal. So notice that the degrees are equal. So therefore, my horizontal asymptote is just the ratio of the leading coefficients, so 1 over 3. Okay, so I have a vertical asymptote at x equals -4/3 and a horizontal asymptote at y equals 1/3. Okay, so the question also asks me to come up with the domain and range. So the domain then is just all values of x such that x cannot equal -4/3, but it can be any other real number. And the range is y such that, now, can y equal 1/3 or can it not? That's what we don't know. Okay, when you have a vertical asymptote, you can always assume that this is the domain, but I can't necessarily assume that y cannot equal 1/3. So I actually have to check, can x plus 2 divided by 3x plus 4 equal 1/3? So for horizontal asymptotes, I have to check if there is a point of intersection. So I can do cross multiplication. So I would get 3x plus 6 equals 3x plus 4. So already you can see there's no solutions to this. There's no way that you can have 3x plus 6 being the same as 3x plus 4, right? If you were to rearrange, you would get 0x equals -2, and that's impossible. So therefore, it never actually does cross the horizontal asymptote. So I can write there that y does not equal 1/3. Okay, but you have to check that first because sometimes it does cross the horizontal asymptote. Okay, so let's try this one. Okay, now you always want to factor if possible. So notice this one has a common factor in the denominator, and that's going to be really important. See, there's a common factor. So this actually reduces to just a half. So this is actually just a horizontal line at a half. Isn't that weird? So there are actually no vertical asymptotes. X minus 3 equals, actually no, I should put the original denominator, 2x minus 6 equals 0, x equals 3. Now, is it a VA or is it a whole? So if I put 3 into the numerator, I also get 0. So it's a whole. whole at 3, a half. Okay, because if I put 3 into the function once it's rearranged, I would get a half. Well, no matter what I put in, I get a half. So there's a whole there at 3, a half. Okay, there's no horizontal asymptote because after I reduce it, I just get a straight line. So even though you could say, oh, the asymptote is 1 to 2, well, that doesn't make sense because the whole line is just a half. So there's no horizontal asymptote because when reduced, it already is just a horizontal line in and of itself. There's no oblique asymptotes. We haven't learned that yet anyway. And then there's no vertical asymptotes either. So the domain then is x such that x cannot equal 3 because there's a hole there, but x could be anything else. And my range is just y equals a half because that's all it is the entire time. So that's there's nothing else. Okay, so we can skip C and D. We need to do those after we know how to do oblique asymptotes. And we can go to example 2. So how can you talk about how a function approaches its vertical asymptote? Okay, so is it going all the way up or is it going all the way down? So the first thing to do is identify what the vertical asymptote is. And in this case, we can see that x equals -2 is the vertical asymptote. Okay, since it makes the denominator 0, but not the numerator. So we can draw a quick little sketch of what that looks like. So basically the question is asking, when I'm coming from the left, am I going all the way down or am I going all the way up? And when I'm coming from the right, am I going down to -infinity or up to +infinity? So to figure that out, you just test x values on either side and see what happens. So on the left-hand side, we'll do that first. So those are numbers just slightly smaller. So let's check like f at -2.1. If you put that in, you get 113. And let's do one slightly closer, 2.01. You get 1103. So clearly it's approaching infinity. So we can conclude from this as x approaches -2, oops, make that look better. As x approaches -2 from the left-hand side, so from the negative side, y is approaching infinity. So as we approach -2 this way, y is going up in that direction. Okay, now we can check the right side. So like f at -1.9, that gives us -107. And f at -1.99 gives me -1097. Now think about why I'm doing 2 points and not just one. Again, it's that whole concept of wanting to show that it's approaching the asymptote, so that's why you do more than one calculation. So here you can see as x is approaching -2 from the positive direction, y is approaching -infinity. So it would be something like that. Okay, and that's how you can test how a function is approaching its vertical asymptotes. Okay, how is this function approaching its horizontal asymptote? Well, first we need to find the horizontal asymptote. So let's rearrange this so that we can see the leading coefficient. So this would be -x plus 2 divided by 3x minus 1. So therefore the horizontal asymptote is y equals -1/3. Okay, so we can draw a quick little sketch. Okay, so remember, horizontal asymptotes have to do with end behavior. Okay, so I need to test very large values of x and very small values of x. So you can just put in like 100, and in this case you get -0.32776. And if I put in 1,000, I get -0.33277. So you have to ask yourself, is that above -1/3 or below -1/3? So as x approaches infinity, y is approaching -1/3, okay, from above, because these are slightly less than 1/3, but in the negative, that would be from above, okay? So from above. So that means you're going to have something looking like this. So as you go to infinity, it's approaching it from above, okay? So now we check -infinity. Now, you might be thinking, well, then obviously if this is from above, then this one must be from below. In this case, that will end up being what happens, but that's not always the case. Sometimes they both approach from above or both from below, so you always have to test. So f at -100 is -0.33887. So you can see that that's going to be lower. And then -1,000 is -0.333887. So as x is approaching -infinity, y is approaching -1/3, but from below. So you need that negative up there. So it looks like this. And there you have it. So that's how you test how you approach horizontal asymptotes. Okay, so remember vertical asymptotes, that's the behavior at exactly that x value, and horizontal asymptotes have to do with end behavior, so on both sides, positive infinity and negative infinity. Okay, so this is the first step in learning how to graph these rational functions, is determining all these different types of discontinuities and also being able to explain why they are what they are. Thanks for watching. I hope you learned a lot.